Within an industrial facility, there may be hundreds of different fluid systems designed to control and direct fluids for a variety of operations. Each system is made up of a series of valves, piping, pumps, and other components. Fluid system components are susceptible to leaks. Two common devices used to prevent or minimize leaks are gaskets and packing. Gaskets are commonly used to seal non-moving connecting surfaces, such as pipe flange faces or the two halves of a pump casing. Gaskets are made of compressible materials that can be squeezed. When a gasket is squeezed between two connecting surfaces or sealing surfaces, the compressibility of the material allows the gasket to form a seal. This illustration shows a gasket between two sections of pipe. The gasket is installed between the smooth sealing surfaces or faces on the connecting flanges at the end of each pipe section. As the flanges are bolted together, the gasket is compressed or squeezed between the faces. As the bolts are tightened, the gasket material is forced into any small imperfections in the sealing surfaces of each flange. As a result, leakage paths are blocked off. Gaskets are made of compressible materials that can be squeezed. When a gasket is squeezed between two connecting surfaces or sealing surfaces, the compressibility of the material allows the gasket to form a seal. This illustration shows a gasket between two sections of pipe. The gasket is installed between the smooth sealing surfaces or faces on the connecting flanges at the end of each pipe section. As the flanges are bolted together, the gasket is compressed or squeezed between the faces. As the bolts are tightened, the gasket material is forced into any small imperfections in the sealing surfaces of each flange. As a result, leakage paths are blocked off. This exaggerated illustration represents a flange with large imperfections in the sealing surfaces, such as deep scratches. A gasket may not be able to fill these deeper imperfections. As a result, leaks might occur. The surfaces should be polished with grit paper or machined to remove the imperfections. This illustration, enhanced to show detail, represents a flange with a high spot. This type of problem may not allow a gasket to compress evenly, creating a leakage path. The surface should be machined to remove the high spot. A cracked flange, exaggerated here to show detail, could also prevent a gasket from sealing properly. If the crack is deep, it may be impossible to repair, and the flange may have to be replaced. If the flanges are out of alignment or the sealing surfaces are not evenly machined, the sealing surfaces may not be parallel. If the sealing surfaces are not parallel, the gasket material may not compress properly when the flanges are connected. One way to determine whether the sealing surfaces are parallel is to measure the gap between the opposing flanges at several points around the flange. If all the measurements are equal, then the sealing surfaces are parallel. Gaskets can be made from many different types of material. Some common materials include metal, Teflon, cork, paper, and rubber. Each type of gasket material is designed for a specific range of applications. Matching a gasket material to an application depends on a variety of factors, including fluid temperature, fluid pressure, and the material's compatibility with the fluids in the system. Though you may not be responsible for choosing a gasket material, you should be able to verify that you have the correct material for a specific application. One way to verify that you have the correct gasket material is to check your company's maintenance procedures. If you're working on a specific piece of equipment, you may be able to consult the equipment manufacturer's manual to determine what gasket material should be used. A more comprehensive source of information can be obtained by consulting a physical properties chart. This type of chart, provided by most gasket manufacturers, rates the physical properties of common gasket materials. Each material is rated according to a list of criteria that indicates how the material will react under certain conditions. The information can help you determine the full range of applications for which a gasket material can be used. There are essentially two basic types of gaskets, flat gaskets and O-rings. Flat gaskets are typically thin, wafer-like devices designed to cover all or much of a sealing surface. Flat gaskets can be pre-formed by a manufacturer, or they can be cut from a sheet of gasket material. Flat gaskets come in many varieties to suit many specific applications. For example, the casing for this low-pressure cold water pump is sealed with a flat paper gasket. This economical gasket has a low pressure rating and is not suited to high temperature situations. It's well matched to this low temperature, low pressure application. The other basic type of gasket is an O-ring. Most O-rings are made from rubber or Teflon and are preformed by the manufacturer. Some O-rings are made using material that must be cut to length and glued together. Unlike a flat gasket, an O-ring is not simply sandwiched between two flat sealing surfaces. Instead, the O-ring is seated on one of the sealing surfaces, typically in a shallow groove. When the opposing surfaces are bolted together, the O-ring is compressed slightly within the groove, seating it firmly in place. This is only one example for seating an O-ring on a flange. There are many other flange variations, but one thing they generally have in common is a special fit that helps hold the O-ring in position when it's compressed. Fluid system components require regular maintenance. Because strong seals are vital to the integrity of a fluid system, gaskets are often replaced as part of any regular maintenance routine, whether they show signs of failure or not. Though many flat gaskets come in preformed shapes and sizes, some common replacement applications call for gaskets that are cut from sheets of gasket material. If the application calls for a circular flat gasket, one way to create the gasket is to use a gasket cutter. This gasket cutter consists of a cutting board with a small hole in the middle, a pin that fits into the hole, and a cutting tool. The cutting tool fits over the pin and has an adjustable blade for cutting the inside and outside diameters of different size gaskets. Let's watch a mechanic use this gasket cutter to cut a circular gasket to fit a pipe flange. Before he begins, the mechanic verifies that he has the correct gasket material by checking his company's maintenance procedure. To prepare for cutting the gasket, the mechanic measures the inside diameter of the flange and the outside diameter of the flange. These measurements will allow him to set the blade on the cutter to cut a gasket that will fit the flange exactly. Next, the mechanic sets up the gasket cutter. He pushes the pin through the gasket material, then places the pin in the hole on the cutting board. The mechanic then positions the cutting blade using the outside diameter measurement so that it will cut the outside edge of the gasket. The outside edge should always be cut first. The mechanic places the cutting tool on the pin and begins the cut by rotating the cutting tool. Once this cut has been made, the pin will still hold the gasket material in place so that the inside edge can be cut. When the cutting tool completes a full circle, the outside edge of the gasket has been cut. The mechanic then removes the cutting tool from the pin and readjusts the blade to the inside diameter measurement of the pipe flange. He places the cutting tool back on the pin and turns it one complete circle to cut the inside edge of the gasket. When the cut is complete, the mechanic removes the tool from the pin. If required, bolt holes are punched through the gasket using a hole punch and a hammer. Once the gasket has been inspected for tears and rough edges, it's ready to be installed. Not all gaskets are circular. In fact, some gaskets form very irregular shapes. Irregular shaped gaskets are typically cut by hand. For example, this low-pressure pump requires two irregular shaped gaskets. Let's see how the mechanic cuts a gasket to fit this pump. First, the mechanic must verify that he has the correct gasket material. He refers to the pump manufacturer's manual for information about the gasket material that should be used. After the mechanic obtains the correct gasket material, he must accurately cut a gasket to fit the shape of the sealing surfaces. In order to do this, he must transfer the shape of the sealing surfaces to the gasket material. This can be accomplished by coating one of the sealing surfaces with a substance that will transfer easily to the gasket material. In this example, the mechanic coats the sealing surface of the upper half of the pump casing with a type of dye called bluing. After the mechanic obtains the correct gasket material, he must accurately cut a gasket to fit the shape of the sealing surfaces. In order to do this, he must transfer the shape of the sealing surfaces to the gasket material. This can be accomplished by coating one of the sealing surfaces with a substance that will transfer easily to the gasket material. In this example, the mechanic coats the sealing surface of the upper half of the pump casing with a type of dye called bluing. The mechanic places the upper half of the casing onto the gasket material and presses down firmly. As he carefully removes the casing, some of the bluing transfers to the gasket material, creating a pattern. The mechanic uses snips to cut the gasket material, following the pattern. Snips are a good tool to use for this procedure, since they can easily cut along the irregular edge of the pattern. When he's finished cutting the gasket to the desired shape, the mechanic uses a hole punch to make bolt holes in the gasket. A hole punch is the best tool for this step because it cuts a clean, precise hole. Well-formed bolt holes are important because they allow connecting bolts to thread easily through the gasket material to avoid tearing or buckling. The mechanic places the gasket on a piece of wood and positions the hole punch over one of the hole shapes on the pattern. He then strikes the punch with a hammer to make the hole. The process is repeated for each bolt hole in the pattern. Once all the bolt holes have been punched out, the gasket is ready for installation. The mechanic then cuts the other gasket for this pump following the same procedure. We've seen two ways that gaskets can be cut. Now try a question on cutting gaskets. In this part, we'll look at how gaskets can be installed. We'll view the installation of a gasket on a pump casing, and we'll see how an O-ring can be installed. Let's start by following a mechanic as he installs a two-piece gasket on a pump. This pump was properly tagged and locked out according to company maintenance procedures. The pump has been drained and vented to remove system fluid. The mechanic needs to install a new gasket between the two halves of the pump casing. This application requires a two-piece gasket made to fit each side of the casing. First, the mechanic must remove the old gaskets. He uses a scraper to remove the old gasket material. As he removes the old gasket, he's careful not to damage the sealing surfaces. When the old gasket material is completely removed, the mechanic disposes of the old material according to company procedure. He then inspects the sealing surfaces for signs of damage. If there are any scrapes or gouges on the sealing surfaces, they must be repaired before the new gasket is installed. Small imperfections may be removed by polishing the surfaces with grit paper. Larger imperfections may require that the sealing surfaces be machined. The sealing surfaces on this pump appear to be in good shape, so the mechanic can install the new gaskets. When installing new gaskets, the equipment manual for this pump recommends using gasket compound on the sealing surfaces. There are basically two different types of gasket compound. They are hardening and non-hardening compounds. Hardening compounds generally dry to a hard finish and often act as an adhesive to hold a gasket in place on a flange. Non-hardening compounds remain soft or tacky. They can function as a sealant to help fill in imperfections on a sealing surface. The manual for this pump recommends using an anti-seize compound. After removing the bluing substance from the casing, the mechanic applies the anti-seize compound to the sealing surface. He applies the compound to the lower half of the pump casing as well. The mechanic then places the gasket halves on the sealing surfaces of the lower half of the casing. He carefully lines up the gaskets with the edge of the pump casing and checks to make sure that all the bolt holes in the gaskets are properly aligned with the bolt holes in the casing. If the bolt holes don't line up perfectly, the holes can be punched again to slightly enlarge them. Forcing bolts through holes that are incorrectly positioned could cause the gasket material to tear, and the gasket might fail as a result. If a gasket is torn during installation, it should be replaced. Once the gasket is properly in place, the mechanic installs the upper half of the pump casing. As he does this, he is careful not to damage the gasket. After the upper half of the pump casing is in place, the mechanic prepares to install the bolts that hold the casing together. He first cleans the bolts and then applies a lubricant to them so that they will thread easily. He partially tightens the bolts by hand and uses a torque wrench to completely tighten the bolts to the torque value specified by the pump manufacturer. The torque value is the amount of pressure that should be exerted on each bolt to achieve the desired tightness. The pump's manufacturer recommends that the bolts be tightened in a specific sequence to prevent damage to the sealing surfaces. This is the tightening sequence for this pump. Like other tightening sequences, it is a crossing pattern. The mechanic follows the pattern, crossing back and forth until all the bolts are tightened to the required torque value. He will repeat this pattern several times, gradually increasing the tightening pressure in several stages. If this tightening process is not followed, the sealing surfaces could warp, or the gasket could be improperly compressed. The pump's manufacturer recommends that the bolts be tightened in a specific sequence to prevent damage to the sealing surfaces. This is the tightening sequence for this pump. Like other tightening sequences, it is a crossing pattern. The mechanic follows the pattern, crossing back and forth until all the bolts are tightened to the required torque value. He will repeat this pattern several times, gradually increasing the tightening pressure in several stages. If this tightening process is not followed, the sealing surfaces could warp, or the gasket could be improperly compressed. Though all tightening sequences generally follow a crossing pattern, not all tightening sequences are exactly alike. The number of bolts and the shape of the flange dictates what the exact sequence will be. The process of installing an O-ring is similar to the process for installing a flat gasket. Let's look at an example of an O-ring installation to see how it can be done. In this example, a mechanic is sealing part of a casing for an oil pump using an O-ring. To start, the mechanic cleans the flange faces and the raised sleeve on the flange that the O-ring fits around. Any foreign material on these surfaces, especially at the base of the sleeve where the O-ring will sit, could damage the O-ring and cause a leak. Once they're clean, the mechanic checks the sleeve and sealing surfaces for any signs of damage. It's very important that the sealing surfaces be in the best condition possible. Even small burrs or sharp edges can cut an O-ring and cause it to leak. Burrs and sharp edges on the flange face can be removed by stoning the surface. Imperfections on other parts of the flange, such as the sleeve, can also be removed by polishing the surfaces with grit paper. The sealing surfaces are in good condition, so the mechanic then checks the O-ring selected for this application to make sure that it's free of cuts or other damage. If the O-ring is damaged, it may not seal properly and should be replaced. Even slight damage or irregularities in an O-ring could prevent it from sealing properly, or could cause the O-ring to fail prematurely. This O-ring is not damaged, so the mechanic can continue to the next step, which is lubricating the O-ring. Many O-rings, due to their rubber composition, have a tendency to stick or bind to metal sealing surfaces. Lubricant is often used to allow the O-ring to seat more easily during installation. The lubricant that's used must be compatible with the fluid in the system and with the material that the O-ring is made of. If the wrong lubricant is used, the O-ring could react with the lubricant and the O-ring could be damaged. Next, the mechanic places the O-ring onto the sleeve on the flange. The lubricated O-ring should fit easily but snugly into position, with just enough room to allow for compression. Once the O-ring is in place, the next step is to assemble the flanges. Care should be taken during this step to make sure that the O-ring is not pinched. Like many O-ring applications, the opposing or mating flange has a special fit designed to help compress the O-ring into position. On this application, the mating flange has a beveled edge that contacts the O-ring when the two flanges are bolted together. The angle of this beveled edge compresses the O-ring evenly against the vertical surface of the sleeve and the horizontal face of the flange, forming a proper seal. Everything looks okay, so the mechanic can install the flange bolts and tighten them in the right order, to the correct torque specifications. When the bolts are properly tightened, the O-ring installation is complete. Now that we've seen the installation of a gasket on a pump and the installation of an O-ring between two pipe flanges, let's try a question on this material. Gaskets are commonly used to seal between stationary or non-moving parts in a fluid system. In this topic, we saw how gaskets work, how gaskets can be cut, and how gaskets can be installed. Now try some practice questions on this material. One way to control leakage around movable parts of equipment, such as pump shafts and valve stems, is to use packing. Packing is generally made of tough fibers that are woven together or pre-formed with other substances into a rope-like material. Packing is typically contained in an assembly called a packing gland. This is an example of a packing gland. Packing, which has been cut into uniform lengths or rings, fits around the shaft, filling the space between the shaft and the walls of a cavity called the stuffing box. A metal plate called a packing follower or gland follower is bolted to one end of the stuffing box. When fully assembled, the gland follower is tightened to exert pressure on the packing and to hold the packing in place. There are several types of packing, each of which can be made out of a variety of materials. Many packing types fall into a common category known as compression packing. Compression packing generally consists of several elements that include a mix of fibers, a binder material, and a lubricant. The fibers can be natural or synthetic, and they're usually twisted, braided, or woven. Binder materials such as grease or wax help to hold the fibers together. The lubricant allows the pump shaft or valve stem to move more easily against the packing, reducing friction and wear. Commonly used lubricants include oils, graphite, and Teflon. To see how compression packing works, let's look at a typical pump application. During pump operation, fluid inside the pump can leak out of the pump along the shaft as it passes through the pump casing. The gland follower is tightened to compress the packing tightly inside the stuffing box. Under compression, the packing is forced against the shaft and the inside wall of the stuffing box. As the packing is compressed, the amount of fluid that can leak out along the shaft is reduced. In this application, the packing does not completely stop leakage around the shaft. A controlled amount of leakage is necessary to keep the packing cool and lubricated as the pump shaft rotates. This controlled leakage is referred to as leak-off. As the pump shaft rotates, it creates friction by rubbing against the packing. This friction generates heat. Leak-off through the packing helps reduce the friction and the heat. Without leak-off, the packing could overheat and be damaged. Severe overheating could also damage the stuffing box and the shaft. On this pump, a metal ring called a lantern ring is installed between two of the rings of packing. The lantern ring provides a means for bringing more liquid into the stuffing box to help cool the packing. Certain applications, such as pumps, generate more friction than others and require this additional fluid to keep the heat that builds up under control. The lantern ring is always positioned under a line called the gland seal line. The gland seal line directs liquid, called seal liquid, into one of the holes in the outside edge of the lantern ring. The seal liquid flows around the lantern ring and through the holes in the ring, where it's then distributed into spaces around the packing and the shaft. This flow of liquid helps keep the packing cool. Leak-off isn't the only thing that keeps the packing from overheating. When the gland follower is tightened to compress the packing, lubricant contained in the packing material is squeezed out. The flow of lubricant reduces the friction between the shaft and the packing, which in turn reduces the amount of heat that's generated. As the lubricant is released from the packing shrinks, and there is more space for system fluid to leak out. When this leakage increases, the gland follower should be tightened to further compress the packing. Over time, the gland follower can be tightened to compress the packing until almost all of the lubricant is squeezed out. As lubricant is released from the packing shrinks to a point where it can no longer be compressed to effectively control leak-off. When this happens, the packing should be replaced. One type of packing that functions differently than compression packing is hydraulic packing. Hydraulic packing is usually made of plastic or all-rubber rings that are pre-formed by the manufacturer. Hydraulic packing rings are generally V or U-shaped in cross-section. Hydraulic packing is typically used in hydraulic or pneumatic applications involving a reciprocating shaft or piston. Hydraulic packing works to create a complete seal that does not allow system fluid to leak out. When hydraulic packing rings are stacked in a stuffing box, they're arranged so that the open end of the V faces inward towards the bottom of the stuffing box. Internal fluid pressure moving up along the shaft forces the sides of the lower packing rings outward against the shaft and the wall of the stuffing box. Fluid pressure also forces each ring against the ring above, causing the rings to expand to fill the stuffing box. This internal fluid pressure actually forces the rings to seal. The gland follower simply holds the rings in place. Now that we've seen how packing operates, try a question on what we covered. Eventually, compression packing wears out or is damaged and can no longer be adjusted to control leak-off. When this happens, the packing must be removed so that new packing can be installed. To show one way of removing packing, we'll use a pump that's been removed from the plant for service. Following company procedures, valves were closed, locked, and tagged out to isolate the pump before it was removed from the system. The pump was also vented and drained. The mechanic's first step is to remove the nuts that hold the gland follower in place. This pump has a two-piece gland follower that allows it to be removed from the shaft. If an application has a single-piece gland follower that cannot be completely removed, the gland follower should be tied out of the way along the shaft. To remove the old packing, the mechanic uses a tool specially designed for this task called a packing puller. It consists of a corkscrew tip, a flexible shaft, and a handle. The mechanic presses the tip of the packing puller against the first ring of packing and turns it until it's firmly embedded in the packing. He then pulls the packing ring out of the stuffing box. The mechanic removes the next packing ring in the same way. He screws in the puller and pulls out the ring of packing. To show one way of removing packing, we'll use a pump that's been removed from the plant for service. Following company procedures, valves were closed, locked, and tagged out to isolate the pump before it was removed from the system. The pump was also vented and drained. The mechanic's first step is to remove the nuts that hold the gland follower in place. This pump has a two-piece gland follower that allows it to be removed from the shaft. If an application has a single-piece gland follower that cannot be completely removed, the gland follower should be tied out of the way along the shaft. On this pump, a lantern ring is positioned between two of the rings of packing. In order to remove the remaining rings of packing, the lantern ring must be removed first. To do this, the mechanic takes a short piece of stiff wire and bends one end to form a small hook. He inserts the wire into the stuffing box between the lantern ring and the wall of the stuffing box. He then hooks the wire onto the edge of the lantern ring and carefully slides it out of the stuffing box along the shaft. Many lantern rings, such as this one, are one-piece devices. In our example, the lantern ring can easily be removed from the shaft. However, in many applications, it's not possible to remove the lantern ring completely. In such cases, the lantern ring is usually tied out of the way. Once the lantern ring has been removed, the mechanic uses the packing puller to remove the rest of the packing. After all of the packing is removed, he checks the stuffing box, the shaft, and the old packing for signs of damage. If there is any damage, it should be brought to the attention of a supervisor. The old packing is checked because it may show signs of damage caused by a damaged shaft. The shaft damage may be difficult to see from outside the pump. Now that the packing is completely removed, try a question on the material. In this part, we'll see how packing can be installed. We'll use this pump as an example with the old packing already removed from its stuffing box. Before installing the new packing, the mechanic cleans the shaft in the stuffing box. Any foreign material that's left on the shaft or in the stuffing box could damage the new packing. Once the shaft and stuffing box are clean, the mechanic's next step is to determine the size of the packing required for this pump and the number of packing rings that should be installed in the stuffing box. To do this, he'll need several measurements. 3 of these measurements are the inside diameter or bore of the stuffing box, the diameter of the shaft, and the depth of the stuffing box, top to bottom. If the packing gland includes a lantern ring, a 4th measurement should be taken to determine the thickness of the lantern ring. First, the mechanic measures the bore of the stuffing box and writes down this value. Next, he measures and writes down the diameter of the shaft. Using these 2 measurements, the mechanic can determine the size of the packing rings using a simple formula. To find the packing size, he subtracts the diameter of the shaft from the bore of the stuffing box and then divides the result by 2. In our example, the bore of the stuffing box is 3 inches and the diameter of the shaft is 2 inches. 3 minus 2 equals 1. 1 divided by 2 is 1/2. Therefore, the size of the packing required for this application is 1/2 inch. Next, the mechanic uses a ruler to measure the depth of the stuffing box to determine how many rings of packing will be needed for this installation. The depth of the stuffing box is the distance, top to bottom, parallel to the shaft. On some applications, it's not possible to directly measure the depth of the stuffing box using a ruler. Instead, the mechanic inserts a stiff piece of wire into the stuffing box and marks the depth on the wire. He removes the wire and measures the distance from the mark to the end of the wire in order to get the depth measurement. Since this stuffing box contains a lantern ring, to get a true depth measurement, the thickness of the lantern ring must also be measured. This thickness is then subtracted from the depth measurement of the stuffing box, and the result is the actual depth that must be filled with packing rings. The last step is to divide the actual depth of the stuffing box that must be filled with packing by the thickness or size of the packing material that will be used. The result is the number of packing rings that are needed. In our example, the size of the packing is 1/2 inch. The depth of the stuffing box to be filled with packing is 2 inches. Dividing 2 inches by 1/2 inch equals 4. So 4 rings of packing are needed. The next step is to mark and cut the packing. The mechanic wraps the packing around the pump shaft a number of times equal to the number of rings he'll need. In our example, he needs 4 rings. He then draws a line across the rings to mark them for cutting. To avoid damaging the pump shaft, the mechanic doesn't cut the packing while it's wrapped around the shaft. He removes the packing and wraps it around a mandrel. A mandrel can be an old shaft or other piece of material that is approximately the same size as the shaft on the pump. Using a sharp knife, he cuts the packing rings on the mandrel along the line he's marked. Before installing the packing, the mechanic coats each packing ring with lubricant. The lubricant makes it easier to install the packing. It also makes it easier to remove the packing when it has to be replaced. The lubricant used must be compatible with the packing and with the fluid in the pump. After the mechanic lubricates the first ring of packing, he positions the ring in the stuffing box and seats it carefully. If the ring is not properly seated, it could be damaged when the next ring is installed. The best tool to seat packing is a split bushing. The split bushing fits inside the stuffing box and around the shaft. It allows the mechanic to seat the packing correctly. When the first ring of packing is properly seated, the mechanic inserts the second ring into the stuffing box. For this application, he positions the cut in the ring 180 degrees from the cut in the first ring. After the mechanic lubricates the first ring of packing, he positions the ring in the stuffing box and seats it carefully. If the ring is not properly seated, it could be damaged when the next ring is installed. The best tool to seat packing is a split bushing. The split bushing fits inside the stuffing box and around the shaft. It allows the mechanic to seat the packing correctly. Depending on the number of rings in a packing gland, the cuts in the ring should be staggered from 90 degrees to 180 degrees apart. Staggering the cuts in this manner reduces the possibility of leakage paths through the packing. In this topic, we saw how packing works, and we looked at how packing can be removed and installed. Now try some practice questions on this material. Once the second ring is properly positioned, the mechanic reinserts the lantern ring into the stuffing box. After the lantern ring is in place, the mechanic installs the remaining 2 rings of packing. He makes sure to stagger the cuts in the packing rings 180 degrees apart and to seat each ring properly using the split bushing. After all the rings of packing have been installed, the mechanic reinstalls the gland follower. He positions the gland follower over the last ring of packing and then reinstalls the nuts that hold it in place. He tightens the nuts just enough to allow the packing to seat firmly inside the stuffing box. Next, the mechanic rotates the pump shaft a few turns by hand. If the shaft is difficult to turn, the nuts on the gland follower can be loosened slightly. Since the pump in our example was removed from the plant for maintenance, we'll look at a similar pump that has been returned to service in order to see the final stage of this maintenance procedure. Once packing has been successfully installed, the mechanic lifts the tags used to isolate the pump according to company safety procedures. The mechanic then restores the valves isolating the pump to their normal positions. He allows the pump to fill with fluid and then starts the pump and lets it run for several minutes. During this time, the packing will absorb some of the liquid and expand inside the stuffing box. After several minutes, the mechanic slowly tightens the nuts on the gland follower, which compresses the packing to obtain the desired leak-off rate. To avoid damaging the packing, the mechanic tightens the nuts in even increments and waits a few minutes after each adjustment to allow the packing to cool off. This technique helps to prevent the new packing from overheating when the pump is first started. Once the desired leak-off rate is achieved, the installation is complete. Now that we've seen how to install packing in a pump, try a question on packing installation. Once packing has been successfully installed, the mechanic lifts the tags used to isolate the pump according to company safety procedures. The mechanic then restores the valves isolating the pump to their normal positions. He allows the pump to fill with fluid and then starts the pump and lets it run for several minutes. During this time, the packing will absorb some of the liquid and expand inside the stuffing box. After several minutes, the mechanic slowly tightens the nuts on the gland follower, which compresses the packing to obtain the desired leak-off rate. To avoid damaging the packing, the mechanic tightens the nuts in even increments and waits a few minutes after each adjustment to allow the packing to cool off. This technique helps to prevent the new packing from overheating when the pump is first started. Once the desired leak-off rate is achieved, the installation is complete.